You know, all around the world, in labs and research institutions, something huge is happening. It's not loud, it's not flashy, but it's a quiet revolution. We're talking about a fundamental shift in how science itself is done. And it's all powered by one simple but totally radical idea: sharing.
So, let's just kick things off with a really powerful question. What if the key to predicting a heart attack, or making medicine fairer for every single person on the planet, wasn't locked away on some researcher's computer? What if it was just out there, for the brightest minds everywhere, all at once?
See, what we're talking about here is this massive global shift towards what's being called open science. It's this incredible movement pushing for more transparency, way more collaboration, and honestly, a radically faster pace of discovery.
And this slide just lays it all out, right? The old way versus the new way. For a long time, science was siloed. Labs hoarded their data, worked pretty much on their own, and progress, well, it could be painfully slow. Open science flips that whole script. It's built on sharing data, which sparks collaborations across the globe and just supercharges the whole process of discovery.
And this quote from a researcher really hits the nail on the head. This isn't just about dumping a bunch of data online. The goal is to build a bridge for innovation and cooperation. Now, of course, you have to balance that openness with smart data management and privacy, but the destination is crystal clear: using data to connect us and solve problems faster.
Okay, so that's the big picture, but what does this actually look like in the real world? I mean, how is it making a difference? Well, let's dive into 3 recent breakthroughs that were only possible because of this open, data-driven approach.
All right, first up, something from the journal Nature Medicine. Let's talk about heart disease, specifically coronary artery disease, or CAD. It's one of the biggest killers on the planet, and for doctors, figuring out who's truly at high risk, well, that's always been a huge, huge challenge.
So what was the solution? It was this incredible new model, a meta-prediction framework. You can think of it like the ultimate risk calculator. It's so smart because it combines the stuff you can't change, like your age and your genetics, with the stuff you can, like your blood pressure or cholesterol levels, to paint this incredibly detailed and way more accurate picture of your personal risk. But here's where it gets really amazing. The model didn't just spit out high risk or low risk. No, it found 5 completely distinct risk groups. And here's the absolute game changer. Each one of these groups responds differently to the exact same treatments. This is a massive leap forward for personalized medicine. It's basically telling us that the one-size-fits-all approach to prevention, it just doesn't cut it.
Okay, on to our second case study. We have these incredible genetic tools called polygenic risk scores, PRS for short, that can predict our risk for all sorts of diseases. But there's a massive, massive problem. Most of the data used to create them comes from people of European ancestry. And what that means is they're just way less accurate for literally everyone else in the world.
So what do we do about it? Well, say hello to Joint PRS. This is a new framework out of Yale that tackles this bias head-on. It's data adaptive, which means it integrates genetic info from many different populations all at once, learning from the patterns they all share. The result? Way more accurate and way more equitable risk predictions for everybody, no matter where your ancestors are from.
And for our last one, let's pull back and take a look at the big picture with some data from the Lancet. Looking at the decade between 2010 and 2019, researchers found some really fantastic news. In almost 4 out of 5 countries, death rates from diseases like cancer and diabetes were actually going down. That's a huge win for public health.
But, and this is a really big but, there's a catch hidden deep in the data. Even though those death rates are falling, the speed of that improvement is slowing down. We're making less progress against some major diseases than we used to. It's a critical warning that we can't take past successes for granted.
Okay, so we've seen what this new way of doing science can achieve. But to really get it, we need to talk about how the tools themselves are getting so smart. Let's pop the hood, so to speak, and take a peek at the mind of the machine. You hear this term thrown around all the time, right? Attention mechanisms in AI. It sounds super complicated, maybe even a little magical. But check this out. A researcher came up with this brilliant way to think about it. He said, just think of it as a k-nearest neighbors algorithm. Now don't worry, that still sounds like jargon, but it's actually really simple. It's just a computer's way of finding its buddies in a giant crowd of data.
Let's actually walk through it step by step. Imagine you give the AI a single word, like apple. That's the query. So step 1, the AI basically shouts out to this massive library of data, hey, who here is the most like me? And it'll find words like fruit, red, and tree. Those are its neighbors.
Step 2. The AI holds a little vote to see which of those neighbors are the most important. Fruit gets a huge vote, red gets a pretty big one, but a distant word like car gets almost no vote at all. And then step 3. All those important neighbors contribute a little piece of their own meaning to create a new, richer, more contextual understanding of the word apple. That's it. That's how an AI pays attention. And that simple process is a total game changer for open science because it lets an AI find these subtle patterns in huge shared datasets that a human could just never spot on their own.
So that brings us to our last section, because none of these breakthroughs just happen out of thin air, right? They're powered by this whole ecosystem of tools and resources that are out there for everyone to use, what you could call the modern biostatistics toolkit.
Inside this toolkit, you've got these super specialized tools like Sig Profiler Extractor for decoding cancer mutations. But then you've also got stuff you might not even think about, like a simple color picker. And that's absolutely vital because, let's be honest, a discovery is useless if you can't show it to people in a chart that actually makes sense. And it's all held together by programming languages like R, which have tools built specifically to visualize gigantic genetic datasets.
And it's not just about the software. The knowledge itself is opening up. We're seeing comprehensive tutorials for R, free courses from big companies like Microsoft that teach you to build AI from the ground up, and even new projects to write the core science textbooks for this new era. It's all about training the next generation of scientists to think and work this way.
So this really leaves us with one big, important question. We have more open data than ever before, and our tools for making sense of it are getting smarter every single day. That bridge for innovation and cooperation, it's being built right now, piece by piece. So the only real question left is, where should we point it? What's the next big challenge we should tackle?